We'll look now at the problem of combinatorics, that is, how to count mathematically. This is why we introduced our notions of factorial and binomial coefficient, was to use them for combinatorics problems. We'll look at two different scenarios, both of which have a similar setup. I'll have a group of n objects, and I'll try and count the number of subgroups I can create. So if I have n objects and I want to look at groups of size k, this is the problem we're interested in. We'll make a distinction between groups where the order matters and groups where the order is irrelevant. So for example, if I have a group of 10 people and I look at possible pairs within the group, if I'm paired with William, the question is, does the pair James-William count and the pair William-James, or are they considered the same? Certain scenarios would say, well, they should be different. For example, if we're trying to create a captain and first mate type scenario, where one of them has a different role than the other. If they're just groups in which each player is considered equal, then the pair William-James and James-William should be considered the same. We have a mathematical theory to allow us to distinguish between the two cases. So let's take a look at what we have here. So if I'm always going to have n objects, and my game is to count the number of groups of size k. When order doesn't matter, I use the binomial coefficient. When order matters, I do something a bit simpler. I do n factorial divided by n minus k factorial. So let's make a remark, which is that n factorial divided by k factorial times n minus k factorial is always less than or equal to n factorial over n minus k factorial. It's because on the left-hand side I have an additional division by k factorial, and dividing by something greater than 1 is always going to make me smaller. Does this make sense? Well, this is saying that in the scenario in which order matters, I have more possibilities. And in the scenario in which order is irrelevant, there are fewer possibilities. I think it makes sense. Let's go back to the scenario of picking pairs of people. If order matters, James and William, followed by William-James, count distinctly. There's two possibilities there. In the case when order doesn't matter, those two possibilities collapse into one. So we should have fewer possibilities in the case where order doesn't matter. And that's reflected in the formula that we have. Let's look at an example. So if I have n equals to 10 and k equals to 3, and the key point order matters, how many possibilities are there? Well, I do 10 factorial divided by 10 minus 3 factorial. Right? This is just the formula n factorial over n minus k factorial. So 10 factorial divided by 7 factorial. And again, I can play this game of trying to cancel common factors out at the top and bottom. So 10 times 9 times 8 times 7 times 6 down to 2 times 1. And I see that everything on the bottom cancels with something on the top. And I'm just left with 10 times 9 times 8, which is like 720. Okay? Computing with the factorials is something we've already looked at in the previous submodule. Now let's just tweak the problem a bit. What if we said the order doesn't matter? Well, this is going to change it from using n factorial divided by n minus k factorial to using the binomial coefficient. So we'll divide by an additional factor of k factorial. So here we'll use, again, n is 10, k is 3. And now we'll use 10 choose 3. So 10 factorial divided by 3 factorial times 10 minus 3 factorial. So of course, this is what we had before. And now I have an additional division by k factorial. So I have so we already know that this is equal to 1 divided by 6 times 10 factorial over 7 factorial. So this is 1 and 6 times 720, so 120. So the number of possibilities goes down by a factor of 6. I really lose a lot when I say the order doesn't matter. But this makes sense because I'm dividing by k factorial. So actually, I know exactly how much it's going to go down by. It's going to go down by a factor of k factorial. So let's look at another example. Here, I'm going to look at codes of length 2 that can be generated from a certain number of letters. So I have 6 letters here, A, B, C, D, E, and that should be F. And I want to look at codes of length 2. So different pairs that I can create here. I won't allow repeats. So once I use one letter, I can't use it again. But I'll say that order matters. So for example, the code AB is considered distinct from the code BA. So how can I do this? Well, this is exactly what our kind of propositions in theory are built to handle. So here I have n equals 6 because I have 6 letters. K is equal to 2 because I want codes of length 2. And order matters. So what do? I do 6 factorial divided by 6 minus 2 factorial. And that's simply applying the formula n factorial divided by n minus k factorial. So I have 6 factorial divided by 4 factorial. Right, I'll write out my factorial, cancel what's possible. And I'm ultimately left with just 6 times 5, so 30. 30 possibilities. Okay? So let's change this up a little bit, but in a way we haven't seen yet. I'm going to change the problem by allowing us to have repeated letters. So instead of saying once the letter's been used in the first part of the code, it can't be used in the second part, I'll allow repeat letters. So I'm going to introduce new possibilities like AA, BB, CC, DD, EE, FF. Those are prohibited in the example we just looked at. So if repeats were allowed, you can think of it in an easier way. I have 2 possibilities, or rather 2 slots I need to fill. The first one can be A, B, C, D, E, or F, so 6 possibilities. And the same in the second slot. A, B, C, D, E, or F, 6 here. I'll multiply these together to get 36. So is this consistent with our earlier example? Well, what new possibilities did I introduce by allowing for repeats? I allowed exactly 6 new possibilities. These are my new possibilities. So 6 new possibilities. And 36 is equal to 30, which is from before, plus the 6 new ones. So our result here is completely consistent with what we saw in the previous example. This also brings us to a new section. We're going to start talking about probability theory. And these kinds of clever ways of counting things are really very important for understanding how to do probability theory well.